When you consider a busy street in a large urban city, what thoughts come to mind? Perhaps honking cabs, cars, or large crowds of people all trying to get to their destinations? Although that picture of a city may seem like a chaotic mess, the reality is that generally, traffic and people move in a relatively orderly fashion. For the most part, cars stop at traffic lights, pedestrians cross when safe to do so, and everything works as it should, even if it's crowded. This system of traffic signals and rules of the road has been in place for many decades, so this type of movement is accepted as the norm for how we get around in a city. But what was city travel like before the invention of traffic signals? There are many stories of pedestrians dodging oncoming cars, horse-drawn carriages and fast-moving cars fighting for space, and just general mayhem ruling the day due to a lack of a well-thought-out plan. There were already rudimentary manually operated signals in operation, but with only a stop-and-go signal, they were not very effective. This left drivers little time to react when the command changed. It was clear when automobiles became more prevalent in the urban environment that a viable solution was needed to lessen the unpredictable nature of traveling in a city. That solution was found in November of 1923, when an inventor named Garrett Morgan came up with the answer. After witnessing an especially bad accident one day, Morgan designed and patented a 3-position traffic signal, which used an automated signal with an interim warning position, the predecessor of today's yellow caution light. With this invention, cities around the world began to adopt this new technology, making the streets safer for cars and pedestrians alike. That fundamental change for city driving came about 100 years ago. Ironically, today, there is a situation in our modern world that is in need of a similar solution, but it will take more than adding a yellow light to solve this new problem. NASA, the FAA, and more than 100 industry partners have tackled the proliferation of unmanned aircraft and the need to regulate and manage these small drones. Just in the past few years, more than an estimated 700,000 unmanned aircraft systems, or UAS, have been purchased and are flying around our skies. With the push for these unmanned aircraft to be used in our daily lives for tasks such as delivering goods to our doorsteps, monitoring traffic on highways, recreational uses, and for medical needs, to name just a few, imagine what our world would look like in a few years if a dependable system of control was not put into place. Many have questions how such a dramatic change to the airspace will affect our lives and safety, and with that, NASA has set out to create a research platform that will help manage large numbers of drones flying at low altitude along with other airspace users. Known as UAS Traffic Management, or UTM, the goal is to create a system that can integrate drones safely and efficiently into air traffic that are already flying in low-altitude airspace. With UTM, package delivery and recreational flights won't interfere with helicopters, airplanes, nearby airports, or even safety drones being flown by first responders. On this episode of NASA X, we will examine this award-winning UTM technology and see how it works, and better comprehend this innovative system. We will also take a look at the dedicated NASA team at various field centers and its government and industry partners to understand the work accomplished developing and testing new software in real-world research. And we will see the system in action and find out when these new innovations will come online. Not too many years after the first flight at Kitty Hawk, North Carolina, NASA's predecessor agency, NACA, began developing technology and systems that have revolutionized the way we fly. NASA took over this workload from NACA in 1958 and has continued to pave a path forward for the aeronautics community ever since. As the premier science and technology agency in the federal government, it makes sense that NASA was once again tasked with understanding and developing a new system to make sure the drone technology would be world-class and safe from day one.
Well, there's a lot of reasons NASA's doing this work, right? So we can have a nice working relationship with industry as well as with the government side, the FAA, the DoD, DHS, DOI, that whole alphabet soup of folks that are interested in this space as well. We can bridge that gap between industry, the public, and them, as well as bring our experience in the airspace and in aeronautics in general to solve the problem, right? So building that coalition, coming up with unique solutions, testing them in the field, making sure that we have all the parties involved. That's really the sweet spot where NASA sits for this kind of thing.
NASA teams have been looking at unmanned aircraft technologies for quite a while, trying to better understand how large, medium, and small drones will begin to be integrated into our national airspace. Early conversations with the Department of Defense just needed NASA to help transition unmanned aircraft into the U.S. airspace. But those needs began to transform to a bigger picture almost immediately.
When we got involved in this, it was a pretty simple problem that we were trying to solve. DoD was bringing unmanned aircraft back from theater. They needed to move them from one base to another. And so the question was, how do you get these very high-performance unmanned aircraft up into Class A airspace? So take off from restricted airspace and move through Class E airspace up into Class A. And that, that's real geeky sounding and all, but for the FAA people, this is really important. So that's what we thought the problem was. After we had started working in this just for a couple of years, along came this package delivery. So a whole new mission and a whole new set of actors came out. So it took on a whole new meaning. NASA then got very interested in how you manage the traffic as well as what the characteristics of the vehicle should be. So when we first started, it was all vehicle-centric. But then as we got real interested in UTM, or UAS traffic management, took on a new meaning of how do you manage all of these vehicles around, and it has just blossomed for that into hundreds or thousands of use cases, and everybody that could possibly think about delivering some service or some product to a household or between businesses now has an interest in the work that we've been doing.
With the knowledge of building a completely new system that would fundamentally change how vehicles move in our airspace, the team needed to carefully understand the major issues. So they took a step-by-step approach to make sure they were moving in the right direction. They first had to lay out the goals, which included, but were not limited to, allowing diverse, small UAS mix and airspace use. For example, package delivery, safely enabling scalability for the future, and establishing a highly efficient, predictable, safe, and affordable airspace operations system, all by developing and validating integration requirements and providing prototype software UTM systems for the FAA to further test.
So NASA developed this concept called Unmanned Aircraft System Traffic Management because we are expecting millions of drones and their operations in a day, which is magnitude order different than what happens with current aviation, where there are 50,000 aircraft, and at a time there are about 6,000 at peak in sky. So the question is, how do we manage these millions of drones without burdening the current air traffic control system? Now, there are fundamental differences in the way the manned aviation works and the drone operations will work. First of all, there is no pilot. Second, that these drones are small. Third, we can actually take advantage of digitization and connectivity across these drones by exchanging information to each other. So the idea of UTM is taking advantage of modern technology, making sure we don't overload the current air traffic control system. Now, one of the big parts of UTM is this managed by exception paradigm. In today's operations, air traffic controller is the only one that has all the information on the radar display. With UTM, we can connect all the information And that information can be shared across all the operators in the sky. That allows us to basically say that just tell me what not to do, and I will figure out a path that will avoid other vehicles in the sky.
As PK mentioned, the system is a bit different than the air traffic control system used by the Federal Aviation Administration for today's commercial airplanes. UTM is based on digital sharing of each user's planned flight details. Each user will have the same situational awareness of airspace, unlike what happens in today's air traffic control.
Well, with the projected number of new drones coming in, the commercial markets for the very large number of drones and operations, it's obvious that the current air traffic management paradigm, a human air traffic controller communicating with one or a handful of vehicles, will not scale up to the number of operations of commercial drones that people are thinking about. And so a new way of controlling this traffic had to be established or thought up. And so NASA came up with the idea and vetted it through the FAA and industry to have this automated system that really did not rely on human air traffic controller interaction. And a key to this is that industry would be providing these services. And this would foster competition and economic growth and such for the system. And so this whole development of this traffic management system, not manually controlled by the air traffic controllers, but by automated systems provided by third-party industry commercial providers, really is a major change in the way air traffic management will be done in this country, and necessary to satisfy the vast number of new entrants in this growing drone market.
You think about the different ways that this system will impact people's lives. One simple one is ordering things online, right? In the future, you may be able to order something. It could be delivered to your house by drone in minutes to hours as opposed to days. That's one use case, right? So people can say, oh wow, that would be neat. Also, you can think about public safety, right? For example, fire departments. One thing they would like to do is to send a drone out before the truck can get there, right? It's possible for the drone to get to a site faster than a truck can, and they can survey the scene before their folks actually arrive. So again, that's a public safety feature that people can usually feel good that our system, a system like we've designed that may be implemented in the future, could help support. So let's imagine both of those things happening at the same time. Someone trying to deliver a hot dog to your house, and then actually a fire happening and the fire department wanting to get through. The system enables those kind of interactions, and it keeps the airspace safe, it keeps things from falling out of the sky, it keeps all the stuff working properly.
To begin problem solving, the team created 4 individual technical capability levels, or TCLs. TCLs are a risk-based development and test approach. TCL-1 served as the starting point of the platform, with drones flying simultaneously at 6 test sites, while each test site operated on their own schedule. TCL-1 focused on areas of remote population, low traffic density, rural applications, and work on notification-based operations. Researchers conducted field tests addressing how drones can be used in agriculture, firefighting, and infrastructure monitoring, and working to incorporate different technologies to help with flying the drones safely, such as scheduling and geofencing, which restricts the flight to an assigned area. After completing these valuable tests, the team then moved into the second stage of the testing, TCL-2. For TCL-2, NASA performed a 5-day flight test at the Nevada test site, with additional flights taking place for the national campaign at an additional 6 FAA UAS test sites. This testing was focused on monitoring drones that are flown in sparsely populated areas where an operator can't actually see the drones they're flying, known as beyond line of sight operations. Researchers tested technologies for on-the-fly flight adjustments in controlled airspace and technology to clear airspace for search and rescue missions or for loss of communications with a small aircraft. As the UTM team monitored these flights, researchers also introduced simulated aircraft into the same airspace occupied by the drones to add more complexity in the system. The drones flew profiles that simulated real-world uses, such as package deliveries, farmland surveys, infrastructure inspections, search and rescue missions, and video surveillance operations. This work was proven successful, and the team quickly moved on to the next phase, TCL-3. TCL-3 was flown at the 6 FAA-designated test sites and focused on creating and testing technologies that will help keep drones safely distanced and flying in their designated volumes.
The UTM project also included the development of onboard technologies to help mitigate the risk from drones, both for those in the air and on the ground. These technologies are designed to help recognize and address potential problems while in flight and without human intervention. One of these technologies allows a drone equipped with special sensors and software to autonomously sense and avoid other aircraft.
This capability level also tested vehicle-to-vehicle communications in areas with moderate UAS traffic density. Testing also included UAS ground control interfacing to locally manage operations, communication, navigation, surveillance, human factors, data exchange, and network solutions. Drones were also flown beyond visual line of sight and in close proximity in altitude and distance. The focused technology flight tests were conducted at Langley and Ames research centers and complemented the flight testing conducted at the designated FAA test sites. Both provided valuable information of the flight performance of the drones necessary to work within the UTM system. Since UTM is a new way to manage air traffic, human factor data collection in real-world conditions is critical to understanding the human-system interactions.
We're really breaking new ground on the way human operators interact with complex systems. And so being here helps us get data on exactly their experience with this system. So for example, we are kind of monitoring the communication patterns that they use. So UTM as a system is exchanging lots and lots of data, and that data can be presented to those operators in a variety of ways. And they also have other ways that are not UTM to communicate with each other. They can communicate with each other over their radios. They can communicate each other through like texting applications, right? So we're kind of measuring all of those communication patterns to see what things are they talking about through UTM means and what things are they talking about with outside of UTM means to really give us a sense for how well UTM as the system is supporting operators in conducting their operations.
Finally, TCL-4 demonstrated how the UTM system can integrate drones into urban areas. Corpus Christi, Texas and Reno, Nevada were chosen as the test sites, offering the right mix of challenges to prove that UTM could work anywhere. The cities have large populations, many obstacles to avoid, windy weather conditions, reduced lines of sight, and fewer safe landing locations. TCL-4 addressed these challenges using UTM systems and technologies on board the drones and on the ground. These include incorporating more localized weather predictions into flight planning, using cell phone networks to enhance drone traffic communications, and relying on cameras, radar, and alternate ways of seeing during flight to ensure drones can maneuver around buildings and land safely, all while communicating with other drones and users of the UTM system.
Over the progression of this project, where we are now is the most complex piece of it, right? So now we are testing in urban environments, in higher density operations, looking at kind of contingency or off-nominal situations. So that list of three things, urban environments, higher densities, off-nominal situations, those are all extremely complicated things to tackle. And so for us to be here tackling those things is the only way we could learn some of the things that are associated with those things. That would be all very difficult to learn in a laboratory setting. There are so many things that are really an opportunity that come from the geographic locations in which we are testing that give us these types of this data, everything that we learn from being here.
Although all this research took place here in the U.S., this new structure will be the framework used around the world.
UTM idea, concept, architecture is out there, and it's been endorsed by ICAO, the International Civil Aviation Organization. And if you look in Europe and in Asia, countries that are starting up their version of UTM, they're starting with this architecture that NASA developed. And so it's really out there, and we're participating in international standards groups to really kind of consolidate what the concept is and harmonize internationally.
The influence of UTM on future projects, I think, was something we're pretty proud of, right? The concept and the way of managing the airspace is really new. And people are seeing application of that to, for example, UAM and air taxis, potentially for high E operations over 60,000 feet, space traffic management. All of these things can leverage what we've learned in UTM because it's about providing services to classes of operations where services aren't provided now and probably won't be provided. Right, so finding a solution to that really has benefited future work as well at NASA.
It's clear to see that a tremendous amount of planning, research, flying, design, and hard work went into this project, and that the UTM framework is here to stay.
I think we're really getting into a whole new era of aviation, right? Where we got completely new operations that weren't there before. We are envisioning a few years from now, maybe 10 years from now, a world where we'll be traveling through cities in small electric aircraft, for example, and we'll have our drones delivering medicine or delivering food or things like that. All this is really only going to be able if we set like a foundation where we can use our great new automation capabilities, networking capabilities, really making use of digital ways to coordinate all these different operations and all this air traffic in a way that just wasn't possible before. But the only way that we can actually do this is by shifting the paradigm entirely from this very human-centered approach that we've been taking over so many years to safely manage all this traffic that was existing for these new operations, to take an approach that is a lot more built around safe frameworks in which the different technologies can interact with each other and where they actually are going to be able to provide the first level of safety layers and the core components of organizing all this traffic.
UTM is enabling airspace operations and providing access to users that was never possible before. It's opened up skies in a way that we can now enable different types of operations in the airspace, and we have a way to manage the traffic because of UTM, which gives tremendous societal benefit of reaching places, cargo as well as people, that was not possible before.
Low-altitude airspace is leading a revolution in flight, and a multi-billion-dollar industry is emerging as a result. At no time in history has aviation been poised to enter the lives of so many people. From package delivery to first responders to safety inspections to video documentation, every person stands to benefit in ways we have only begun to imagine.
We're really at a once-in-a-lifetime opportunity to be part of aviation. We see new aircraft that like we've never seen before. We have new types of software systems, scalable and cloud-based. We have new companies that are entering the space that we haven't traditionally seen in aviation so far, and we have really great collaboration amongst industry to work together, as well as collaboration with the FAA and aviation authorities to go ahead and make that happen. And that really sets us up for the next 100 years of aviation in a way that we haven't seen before.
The research and development completed on the UTM project has come to a close, but that doesn't mean that the final chapter of this technology has been written. NASA and its partners are planning future research and testing to mature these systems to the point that one day soon, flying drones in our neighborhood will be as common as seeing yellow caution signals on traffic lights. With the success of NASA's UTM project, that day is much closer than you may think.